Page 21 of Complex Numbers and Polynomials. This is the last page. Number 5. A scientist is trying to design a crash test barrier with the characteristics shown graphically below. The independent variable t is the time after impact measured in milliseconds such that t is between 0 and 700. The dependent variable is the distance the barrier is depressed during the impact measured in millimeters. Okay. The equation for this graph has the form kt times t minus a quantity squared. Use the graph to find a. What does this value represent? Okay, so if we know that this function here is representing this shape, we know that there are two zeros. So that means it would correspond to the zeros for t here, right? So according to this graph, it should have a 0 at 0, and it should have a 0 at about 700 because it touches at 0 and 700, which means A should be 700. So what does 700 represent? 700 should be the number of milliseconds after the impact, right? And the barrier is no longer what they call depressed, or like, I think they mean like smashed, right? So like, how much is the barrier smashed? Well, at time equals 0, it's smashed 0 because the impact is about to happen. Once the impact happens, then the barrier gets smashed. The most it gets smashed is about 120 units on the y-axis, and then maybe the car kind of bounces off the barrier, and then after 700 milliseconds, it is not smashed at all. So what does A represent? Well, it's 700 milliseconds, which is the time after the impact that the barrier stops being smashed. If the ideal crash barrier is depressed by 85 millimeters after 100 milliseconds about here, okay? Find the value of k. Okay. So k is a constant, it's not a variable. So we can, like, they already told us exactly what the function looks like. It looks exactly like this. So in this case, they already know what k is and have graphed it. Now we're going to do the opposite. We're going to take one of the points on the graph, which is 100, 85, and we're going to use that to figure out what k is. So how do we do that? We just substitute in y equals 85 and x equals 100, or 85 equals function of t, f of t, and t equals 100. So let's do that. So we'll say 85 equals k times t. Oh, t is 100. K times 100 times 100 minus a, which is 700, right? Squared. So k times 100 and negative 600 squared. Oops. Okay. And so, whoa, that's like negative 600 squared is like 3600 or something. Negative 600 squared is positive 600 squared, which is 360,000 times an additional 100. So it's like 36 million maybe. 36 million. Okay. So we got 85 equals 36 million times k. So k is equal to 85 divided by 36 million. So the answer is 2.36 times 2.36 times 10 to the negative 6th. So that's k. So we just substitute k in and we say, okay, f of t equals 2.36 times 10 to the negative 6 times t times t minus a, which is 700. By the way, if you look at the book answer, they just leave 2.36 times 10 to the negative 6 as a fraction. They just leave it like this instead, which is fine too. Okay, remember in IB you always want to leave 3 significant figures. Number 7, a ladder of length 10 meters is leaning against a wall so that it just touches a cube of edge length 1 meter as shown. What height up the wall does the ladder reach? Okay, so this is one of those trig problems, and probably we're going to use Pythagorean's theorem or something. So if you look at the big triangle that I'm going to trace out here, one of the sides is 10, one of the sides is x, and the other side on the bottom is 1 plus a little piece right there. So we'll call that 1 plus y. And then so we'll write the Pythagorean's theorem equation. It will be x squared plus 1 plus y squared equals 10 squared. Now what we need to do is we need to get rid of one of the variables, like the y, for example, because we want to know what the x length is. We don't care about y. So can we make another equation which uses maybe proportions or something to express y in terms of x? I think we can. So let's do this. We're going to make one equation which has maybe look at this little triangle here. Let's make an equation that is has the sides of that little triangle. So I'm going to make a ratio of the opposite and the adjacent of this little triangle, or like the two legs of this triangle. The little leg is y, right? And the big leg would be 1. And that will be proportional to like this triangle. I could do the same thing for this triangle. I could put the little leg on top, which is 1, and I could put the big leg on top, which is x minus 1, right? Because like this length here is x minus 1. So there I've just made an equation which has related y and x, which is very handy to get rid of y here. So now I'm going to substitute it in. So I have 1 plus 1 over x minus 1 squared equals 100. Okay, now your urge instinct is going to be to expand this and like solve for x explicitly. But remember that this is probably going to be like a paper 2 type problem. So what you want to do is like solve it using the calculator. And to solve this in the calculator, all you have to do is put the left side and the right into y equals. So the left side we're going to put in at y1, we'll put x squared plus parentheses 1 plus 1 over x minus 1. There's a mode you can go into here to make like a fraction. So 1, then you don't have to use so many parentheses. It's kind of annoying to do so many parentheses. Squared. Okay, so that's one side, and the left side would be 100. And what we want to know is when these intersect on the graph. Now, that's a pretty weird looking function, isn't it? We're more interested in here where it we want to see where it crosses 100, which is way up here. So let's do window, and we'll make the y value equal, the y max equal 100, and then we'll graph again. There's our 100. And so we're going to get two intersections right around there. Okay, and let's do this. We're going to change our window size. We'll graph, instead of from negative 10 to 10, we'll graph from negative 4 to 4. We'll graph between negative 90 and negative 110. Then we'll be able to see the intersection a little bit better. There. So there's the intersection right there. So let's find the intersections by doing second calc intersect. First curve, the squared curve, yes. Second curve, y equals 100, yes. Guess. Put any guess because, okay, and we found the left one first. The first intersection is 0.909. Okay, so one of the possibilities is x equals 0.909. The other possibility, let's repeat second calc intersect again. Oh, first curve, x squared, yes. Second curve, y equals 100. I meant y equals x squared. Guess, and let's move the cursor to the right side so that we can get the right intersection. The right intersection is 1.11. So we have two possibilities. One is that x equals 1.11, and the other is that x equals 0.909. If you look at what x represents, it is the height of the ladder. 1.11 would kind of look like this, right? You would have the box here and the ladder is like very leaned over, right? That would be 1.11, which would be slightly larger than the box. X equals 0.909 is kind of a weird solution. It's like, what would that be? It's like this, because the ladder is like touching at a height that is even lower than the box. That makes no sense, right? So this solution is invalid. Is there any other solution? I think there should be a solution where the ladder is kind of like the way it's drawn here. Actually, if we zoom out, we can see that there's another intersection here. So let's find out what intersection that is. So second calc intersect. First curve, second curve, guess. Okay, oh, there it is, 9.94. So the solution that matches the picture would be 9.94. Okay, so there's actually three zeros, one, two, or not three zeros, but three intersections, 1, 2, 3. There's probably one over there too, but only two of them are valid because we want an x value that's greater than 1. So we would choose 1.11 and 9.94.